Brandon, if you don't mind. Thank you, sir.
This is good. Good to brush up on our.
So, here's where we are. This is what we already have in symbols. This is what we already have on the board. So the kicker is to knock this down and make it applicable for averages. What do we need to apply as a multiplier? So we had to vote for z, which is a perfectly logical thing. I mean, if the z was a good multiplier for the proportions, why don't we just use a z for the averages as well? So here's the question I have for you. Why did we use the z for proportions?
Because x and y were already taken with other things.
Because x and y were already spoken for, accounted for. Because we kind of developed it. Where did it come from? I mean, the entire time we were talking about proportions.
Z was based off of our. Now I feel on the spot.
Go on, please, please.
Wasn't Z based off of how it was a percentage?
It was your confidence.
Yes.
Right. 1 was 68, 2 was 95. Good. Now, but can I go back even further?
Yeah.
Why was it okay to bring Z in? We were talking about the binomial. This is all binomial stuff. Right? Ones and zeros, heads and tails. Which is not based on Z, that's based on the binomial. Where did Z come from? It's okay, it has been a long time. And the z-score is what Dawn is talking about, as far as 1 is 68, 1 standard deviation, 2 standard deviations, 95. But why is it okay to mix z in with the binomial? Do you remember? It's okay, you can say no. Kate, go ahead.
Oh, I was just saying it was our z-score. We're good.
Oh, good, it is the z-score. The thing was, do you remember, and if you can say no to this, which is why I've got it archived, you can go back and look at it again. The problem with the binomial is, in order to set up the standard deviations to be symmetric, you had to assume the binomial had a percentage very close to 0.5. As soon as it deviated from 0.5 at all, remember what happened to the curves? They got skewed. So by increasing the sample sizes, we pulled the skew out, and they got their symmetry back. So when the sample sizes are large enough, essentially, when this guy is large enough, and there was a definition for large enough, we talked about it briefly in class, don't have to worry about it too much. When the sample sizes are large enough, this bad boy is okay to use. Here's the problem, and the historical problem with the distribution we're about to do. It does have a history lesson tied to it. So go ahead and read this. This was a newspaper article from 1899. Dublin today. I've never heard that before.
That's funny. Sounds like you're seeing how to play.
Yes. Rednecks and Southsiders need not apply. That's from the movie The Commitments. You ever seen that movie? It's fantastic. They dropped the F-bomb, I think, 162 times in an hour and a half. It's awesome. So this is steeped in historical facts, friends. In 1899, the Guinness Brewery had a problem. They had a problem. And the problem was simple. They needed a statistician to be able to analyze quality control of a lot of different things, everything from crop yield. You gotta remember, this is when Guinness was essentially the BBC. This wasn't like Guinness as it is now worldwide. You can find it in 7-Eleven. This was Guinness when it was just in Ireland, and there's they're making like 3 bottles a day or something like that. So we needed this quality control, but the problem with quality control was they were so small, they couldn't drive their sample sizes up high enough to deal with the inevitable shifts of bias that happen. That's the issue. Whereas with the percentages, it's easy. Just go out and collect more data. Yes, no, 1, 0, 1. It's pretty simple to gather more data percentage-wise. It's not always easy to get a more significant measurement or a more precise measurement. It also costs a lot more sometimes. Most of the studies you're going to see in your lives are based around percentages and not averages. And one of the big reasons is it's really easy to call somebody and go yes or no, yes or no, yes or no, yes or no. It's extraordinarily hard to go up to somebody and go, I need to weigh you. Come here, take your clothes off. Get on the scale. I mean, it's a time-consuming process, not to mention the fact you might get punched in the face. So the idea is you can't always just drive up your sample size. Sometimes you have to deal with the sample size as it is, and it might be small. And that was his challenge. That was his challenge. And some of it was consumption. You know, and you can't, you know, if you only have 4 bottles of beer a day, you can't drink all 4 of them, you can't sell anything. So his solution was very, very clever. He said, you know what? Okay, the Z is out there, it's been around since the time of Gauss, 150 years before me, but I can't use it. I can't use it on small samples. Let's make up a new one that does work on small samples. And that might sound like a bit cavalier, like make up statistics. We'll do it as we go through this course. It's actually an awesome thing to do as long as you take randomness into account. So he did.
Is that like when we just decide our P hat and Q hat are 0.5 and 0.5?
No, well, that's what, if you test against that, that's a different story. But what you do is you set it at 0.5 and then you see if the data shows that it is 0.5. And it is just like that. It's Monte Carlo simulation. We do a lot of them in this class. So here's what he did. He created what's called the student's T distribution. And it's usually just called the T distribution, historically. The reason it's called that and not the G for Gossett distribution, apparently Guinness wouldn't let them publish under their own names. I guess some kind of corporate hierarchical thing. But anyway, the problem with the Z distribution was you had to assume a mu and a sigma, which were too widely variant on small sample sizes. So he said, well, what the hell? Let's make the sample size be the variable. And this is what it came up. You have to realize that's the formula for the T distribution. The Z distribution's got a formula too. I've intentionally hidden it from you guys. It's half as complex as this one. The most amazing thing is he came up with this by Monte Carlo simulations using paper pulled out of a hat and looking at trials. Now you guys have the benefit of a computer running Excel. So every time you guys hold down the F9 button in a project or something you've done for me, you're doing what Gossett did without the hat and paper. You're letting the hat and paper be ones and zeros in the machine and keep it track. But you're doing essentially what he did 100 plus years ago. Pretty rad, actually. Pretty rad. So his idea was to develop this distribution, which, now what I want to do is, I want to take a look at this so you see what it looks like. Because that's a great formula, except for the fact that it probably gave you all agita when you saw it. So, oops, hang on. Yes, you can. It's right here. So, take a look at this. Now, what you're looking at are 2 curves. 2 curves. And oh, thank you, Jason. That's perfect. What you're looking at are 2 curves here. The red curve is the T curve that Gossett proposed. The blue curve is the standard normal distribution that you have always used. It's the one you've always used. So in other words, if you go from -1 to 1, and you go straight up, you've trapped 68% of the data between -1 and 1. If you go between -2 and 2, and you go straight up to the blue curve, you've trapped 95% of the data. If you go -3 to 3, you've got almost all of it, so forth and so on and so forth and so on. And on the left, you might be looking at this over here. All this is the X and Y values that I used, so the horizontal and the vertical values. Excel is kind of a pain in the ass for doing this kind of stuff. You have to actually make the graph point by point and then connect them, which is totally fine, it works. Okay, look at the red curve, which is the T curve. Now this is a very small sample. Sample size is only 2 right now. 2, very, very small. How is the T curve similar to the Z curve? Symmetric. Love that. It's perfectly symmetrical. That's a function of the function. If you look back at that equation, it's got an E in it, just like the bell curve formula, and that beautiful symmetry of E raised to a squared power takes care of that. Thank you, D. Very nice. Very nice. How else is it similar? There's one other way I can see that it's similar. It is symmetrical. It has the same center. Thank you, Laura. They're both centered on the 0. That was key because we want that. We want symmetry. But we want symmetry around a not positive, not negative, but 0 value, because then we can do symmetric pluses and minuses from that. Go, Kate.
Is there anything special about the fact that they cross at 2 standard deviations, or is that just random?
No. It's actually not exactly 2, it's a little shy. But can we focus, what Kate just asked, is there anything special about where they cross right here? Instead of focusing on the mathematics of where they cross, look at what happens to the left and right of where they cross. Like, for example, by 2 standard deviations-ish, it looks like if we move to the right, the red curve is below the blue curve. Which means, friends, if we go -2 to 2 on the blue curve, we've chapped 95%, yes? How about on the red curve? Less. Key. It's less than 95% on the red curve. Which means, in order to pick up 95% confidence, we're going to have to go wider to add up the area to get 95%. Now, that's a sample size of 2, of course. Now, you would expect that, yes? With a sample size of 2, with only 2 data points, even if they're really good data points, what do you have to accept? Offness. You have to accept lots of offness, yeah? You've got to accept the fact that even though you've got 2 good data points, chances are they're not both close to average. You've got some wild variation. Variation that will begin to tame itself, as you sample more. And that's the genius of this curve. Right now, I like to call it has fat tails. It's got fat tails. Because of small sample sizes, you have to put more area out in the tails because you have to sacrifice confidence in the middle. But look what happens as we start increasing the sample sizes. See that jump? There's 2, there's 3, there's 4, there's 5, there's 6. It's beginning to what? Yes, it's beginning to approximate the bell curve, and that's a function of the function. As n goes off to infinity, that crazy formula that you saw, that Gossett developed, limits to the bell curve. As a matter of fact, there's an old number, I mentioned this in 243, there's a number 30, that once you get to essentially a sample size of 30, the curves are arguably the same thing. Now, you don't have to memorize that number, it's an indicated number anymore. It used to be back in the day, that when the sample sizes were below 30, they said use the t-distribution. When they're above 30, use the z-distribution. You know what I say? Use the t-distribution whenever you're doing an average. Because if both z and t work above 30, and if only t works below 30, why not just always use t? Does that make sense? And when I say use t, technology is going to be doing this for you for the most part. So right now, this is the curve that we're on. This is the curve we need, right? Because we have 30 burritos. 30 burritos. I got a thing over here called degrees of freedom. I put that in kind of as an afterthought. It's a bit of an antiquated term that doesn't really apply to you guys as much. Those of you going on to more and more statistics classes might see it again. And I've got some homework questions about it if you're interested. It's 1 less than your sample size, by definition. And there's a write-up in your homework if you're interested as to what they are, and if you ever need it again, you'll know where it is. But here's the question. Sample size of 30, do you see how the red and the blue aren't exactly the same?
So if you get 31, will it match it perfectly?
It's not 31. It's not a whole number of n that actually makes them match, but I used to know what it was and I don't. I think the idea is, as it goes to infinity, it matches perfectly. It'll always be off a little bit, like asymptotic, if you will. And if you look at this column versus that column, you see the slight differences in the values, even at sample sizes of 30. Now, here's the deal. Here's the deal. Can I shut this down real quick? Oops, that's never mind. Back in the day, oops. Back in the day, let's see if this loads. I think it will. Yep, that's good. We had to use tables. Now, I've intentionally hidden all this stuff from you guys. This is how I didn't want the course to look. This is how a lot of stat courses are taught. Remember STEM normal?
Yeah.
STEM normal takes care of that and that.
Thank you.
Well, you're welcome. It's my pleasure because there's no sense in forcing you to go through a... It's funny because I guess this bears talking about. I've gotten discussions with statisticians about, you give them a program to run the norm, teach them how to use the tables. I'm like, well, nobody's doing calculus. Not with the tables, nor with the program. So what's the difference?
So people really just use the tables?
Oh, God, yeah, for sure, for sure. And I always share the program, and half people I talk to love the program, half hate it. And it's one of those ethical things, not ethical things, it's a pedagogical view thing. I mean, the tables are a shortcut for calculus. All the tables are shortcutting is shading under the curve, which I made you guys do on the first day of STEM normal. We drew the bell curve and we shaded. How much percentage? How much percentage? All the tables are is a shortcut for that. The reason I'm going to take you away from the t-table in a minute is because it's slightly confusing. The t-table has a degrees of freedom column, and it has to have this because that's dependent on sample size. This is going to be 1 less than your sample size. So for us, we would have to use 29 degrees of freedom, which is 1 less than our sample size. So our t multiplier is somewhere in this row right here. I can't highlight it right now. There it is. One of those numbers is our t multiplier. It's either 2.756, 2.462, 2.045, 1.699, 1.311. Which one is it? Well, then you have to use the top row to decide. So you have to go up here. And you're looking for area in 1 or 2 tails. 1 tail area doesn't make any sense yet to us. It will by next week. 2 tails. how much area, now this is a bit of a backwards question. If we want to be 95% confident, which I'm assuming we do, how much area is in the tails? 2.5 in each, so 5% total, yeah? 5% total area in the two tails. So we need to use the middle column. We need to use that 0.05. We're going to scroll down here. We're going to use 2.045, which is slightly bigger than the 1.96 we would use with a normal curve. You see the difference there? So it's slightly larger than the 1.96 we would use. So the answer to all of this, and I see like just the energy draining out of your face, is good. That's the whole point. We don't do it like this anymore, because this is where stat goes to die.
I feel like you're just,
Go ahead.
I just feel like with the table, you just kind of have to assume that they're right.
Well, trust that it is.
They teach you how to use it.
Yes, it is right. Well, Kate's question isn't the pedagogy, it's the table. Your results are only as good as the table you
It's
use.
just like a calculator.
It is exactly like that. You're assuming the calculator's kicking the right numbers out. And you could get these exact numbers using your machine. Absolutely. They would come, it's just that they're all in one place for you here. And I love when Diaz said that, because it is exactly the same as using a machine. It's just you're already used to holding this in your hand, the rest is on the other table. So, what we would have to do, friends, let's shut this down for a second, actually, go back to this slide. This is the kicker. Whoops, I guess I didn't animate this correctly. Oh, here it comes. So, if we're estimating an average, your center is x bar, that's the key right there. The multiplier becomes t. That's your margin of error calculation that we need. And the idea is, just like with proportions, that what you're looking for, in this case mu, is going to be somewhere between your center minus that margin of error and your center plus that margin of error. That's the idea. 95% confidence that what you're looking for, the parameter you're estimating, is between a margin of error above and below your sample center.
What does it say under that red circle at the top of the fraction?
The red
It's
circle.
S over.
Oh, God, yes. Sorry. Let me just do
B
this. Makes
times
it
S
easier.
over root n.
Let's just make that. That makes it easier.
Yeah.
Oh, there. Sorry. Yeah, it's S over, but you guys already figured that part out. The S over root n you had dialed. You had it dialed. You figured out the same, JC, you figured out sample standard deviation's got to be in there. So does the sample size, Lauren, because of precision. The kicker was, why is this t? Well, because it has to be. Because you can't just force a z curve where a t curve should be used. And this is your first new distribution. In 243, we had the binomial, and we had the normal. This is the first new one of 244, the t distribution. Now, real quick, what I'm going to... Oh, Renee, go. Please. Are you sure? You probably... Maybe. Ish. While you guys are diligently taking notes, which of course you don't have to do because I'm going to have the PowerPoint for you. But whatever, you don't have to, I'm just saying. I'm going to calculate this one out using this margin of error formula real quick. I'm going to do it up here on the TI. So the multiplier we had to use was 2.045. That was that t multiplier. Times, that's divided by, times, I'm going to cheat and use the statistics menu to pull up standard deviation. Times standard deviation, and then I'm going to divide that by the square root of 30. That is what our standard error is. And that's in pounds. That's in pounds. So remember what our average was, the X bar? How much a Del Taco half-pound beef and cheese burrito weighed? 0.526, I think it was, pounds. So, yeah, good. That's your pound weight. Michael, go.
Would order of operations go into that at all?
It would, but because it's all multiplication and division, left to right is fine. Yeah, Michael's got a good point in that, technically speaking, I probably should have put parentheses around the multiplication before doing the division, but that's going to happen first anyway. Or I could have grouped the division into the S and then multiplied by the 2.045, but that doesn't matter either because of associativity. Yes, in general, your answer is correct, but it doesn't have to worry about it here, if that's fair. Kate?
Where did you get your lowest stuff?
Don't you worry about that. I'm doing this just to get some numbers up for you. It's in your VARs menu. If you press VARs, there's a statistics sub-menu. It's all buried in there. You're not going to need it because you're about to see why. There's a built-in in here for you. But what I want to do first is I want to kind of do this out by finding, now watch this, I can do, here's right here, Kate, bars, statistics. If I do the average minus that previous answer, that means I can be 95% confident. I can be 95% confident that the average weight of a Del Taco half-pound bean and cheese burrito is at least that much. That's my low end of my confidence interval. It's the center minus the margin of error. You guys seeing why this is a margin of error up here? That's the margin of error. Okay. It's a 2-ish, 2 standard deviations, or 95% confidence t-score times the standard error. So it's at least that much. Could be as much as, whoops, x bar plus that. So I'm 95% confident that my weight of a Del Taco half-pound bean and cheese burrito is at least 0.517 pounds, but no more than 0.535 pounds. Which means, how do I feel about Del Taco naming their half-pound bean and cheese burritos half-pound bean and cheese burritos? I feel good as long as they mean their half-pound bean and cheese burritos. Give me 2 more words. I'm coughing up chlorine. Give me 2 words, one of which is on. On average, yes. We cannot guarantee that every single burrito coming out of that store is a half a pound, as we saw from the data, yes? Some of those are 0.49s. Then you're going to go, oh my God, it's 0.49. I know, this is American, litigious, right? And that's a high percentage, 7 in 30 or under? That's a high percentage of underness. Now who's carrying around a scientific scale in their car to measure in the drive-thru? Probably nobody.
You do?
On my bike, on an amplifier. But the idea is, as long as we're talking about on average, yes, I am happy saying that they are more than half a pound, because they are more than half a pound on average. Go, Renee, please.
So, by them saying it's half a pound, then they're on average 99%?
You could actually bump it out, couldn't you? If you wanted to use a higher confidence, chances are they are, which means we'd have to adjust this 2.045, yes? Guess what? We're done doing it this way. I mean, forcing you guys through the derivation of t and using the t and the margin of error, that's just silly. Turn the projector off, grab your TIs, let's show you how to get these numbers without going through all this incremental stuff, putting it together. I'd much rather you focus on the interpretation of the result, but I hate just being like, guess what, you gotta use t now. I mean, there's a rich history as to why you have to use t. I wanted you to see that history, so now you know it. It has to do with Guinness, which is kind of fun. So grab your TIs, 0.517 to 0.535. I can commit that to memory, which means I